Modeling a curve with straight line segments is actually a remarkably effective way of representing the shape. And straight lines are significantly easier to deal with. We can calculate, for instance, the area enclosed by the trapezium which the straight line represents. If you drop a line perpendicularly down from the two endpoints of your straight line segment, then you form a trapezium where the two vertical lines are parallel because they're both vertical, so they can form the two parallel lines which are more traditionally the top and the bottom of a trapezium if you draw it the usual way around. We can find the area of that really quickly, and we can calculate the area of multiple trapezia. We can even combine them into a neat little formula so that we don't have to do quite so much work one at a time. We can split our interval into more trapezia if we like, and that will give us a more accurate representation of the area. Think of this as checking in with the function more often. So instead of heading out and going blind for an entire interval of 1 along the x-axis, maybe you only go a half, and then you see what the function is doing. You try a half squared. Oh, that's only 0.25, so I'll head to there in a straight line, and then I'll check in again half a unit later and see where I get to then. The upshot of that, it's more like a dog following their owner, not looking up except every 10 seconds or so. You're going to get a less accurate following of the path than if the dog looks up every 5 seconds or even every second and readjusts their path. So you're being more closely followed in this case if you have a large number of strips. And of course that means that the area approximation will get increasingly good as the number of strips increases. Every individual trapezium contributes less and less to the overall total, so the fact that it's not quite accurate becomes less and less important. And yet there are more and more trapezia involved. This is the essence of integration as well. Really, what's going on behind the scenes when you integrate is taking this to its extreme. Imagining what would happen if you had an infinite number of strips, and every strip effectively then has an area of 0. It's like adding just a line rather than an actual solid piece of area. And for that reason, we can get pretty good results just by choosing a largish value for the number of strips. There's something else interesting though. It's not just a decent approximation, it's an overestimate. So if we look at the true area of 8/3, we've got an overestimate when we have 3 strips of about 5%. That overestimate gets smaller if we increase the number of strips, but it's still an overestimate. We're getting 2.68 instead of 2.66. And even though we keep getting better when we increase the number of strips, we don't ever drop down as low as the true area. We can see that in reverse as well. If we look at what happens when you've just got 2 strips, we now have an error of 12.5%. And the reason now becomes clear. Look at the curvature of x squared. We have a convex curve here. In fact, x squared is convex everywhere. It's convex when x is negative as well as when x is positive. So no matter where you choose to take your integral, you will always find that trapezium rule gives an overestimate. Of course, we can improve on this by having more strips, but it's worth being aware of the fact that trapezium rule is always going to overshoot the curve because the curve has a constantly increasing gradient. It's going to be going faster at the end than it was at the beginning, so it's going to undercut the straight line that we're using to approximate it. Let's see what happens with a function that has some concavity and convexity in it. So we've got something weird going on here. We get a true area of 0, which makes sense. We're integrating from -2 to 2, so the positive and negative bits cancel out. The trapezium area is also 0. That's where the error is coming out as something strange. We're trying to divide the trapezium area by the true area to get a comparison. But we can see these two are the same, so our trapezium area is doing a pretty darn good job of approximating this area. But if we change this just a little bit, we find that's not necessarily quite the same anymore. We've got a trapezium area which is smaller than the true area, and now we've got a trapezium area which is larger than the true area. Now it may seem a little strange here. The trapezium area in terms of the size of the area, regardless of sign, is actually smaller right now, but we'd still think of it as an overestimate because what we're using trapezium rule for is not simply the area under the curve, but the size of the integral. So the sign matters. And £46 in debt is richer than £47 in debt. Now, if we reduce the number of strips, we can still see the same kind of effect happening here. But this becomes clearer if we take a function which doesn't have weird negative bits going on. So let's have a quick look at ln x. If we integrate here, we can see that we're going to get an underestimate. No matter how many strips we choose to use, we always get an underestimate for ln x because it is concave everywhere. Wherever the function exists, the gradient of the function is decreasing. And that means that no matter how quickly it was increasing, no matter what the gradient was at the beginning of a particular trapezium, it's going to be more shallow at the end, and the straight line will undercut the curve. If you're asked to describe this or to explain why your answer is an overestimate or an underestimate, the easiest way to do it is to just draw a picture of the curve. If they're talking about e to the x or x squared, then you draw yourself a convex graph like this one, and you demonstrate by drawing a nice straight line on it why any strip that you produce will be an overestimate. And then if you're looking at a curve which is concave, then you draw yourself a trapezium and you demonstrate that it's always going to be an underestimate.